Foot and mouth disease affects cattle, sheep, pigs and goats and poses a major threat to livestock in most parts of the world. Its impact can be devastating. The 2001 foot and mouth disease outbreak in the UK was a traumatic episode for the whole nation, but particularly for farmers. And it was expensive. It inflicted costs of over $8 billion. The disease is caused by a virus, a tiny package of molecules that makes copies of itself inside the cells of infected animals, and then spreads to new hosts. So what can be done to control the disease? There are vaccines against foot and mouth disease, but they're not always used to control epidemics because of certain technical and political problems associated with their use. So we're interested in looking for new ways in order to control the disease. And one possibility is to try and develop antiviral drugs that would stop the virus from replicating inside infected animals. An interesting target for drug design is a viral protein known as the 3C protease. This is an enzyme that cuts the virus polyprotein into the pieces needed to make new virus particles within infected cells. If we can find a drug that attaches to the 3C protein and stops it from working, we may be able to block the infection and stop the spread of the disease. But drug discovery is a very costly and complex process. The first step is to try and figure out what the 3C protein molecule looks like so that we can design a drug of exactly the right shape to stick to it and so block the action of the protease. But that's very hard to do because protein molecules are extremely small. They're too small to see even with the most powerful microscopes. 3C is about this size, but we need to make it this size in order to have a really good look. To solve this problem, my lab has used X-ray crystallography. This is an elaborate technique, but a very powerful one. We start with a copy of the DNA that codes for the virus's 3C protein.
Having the DNA allows us to make the protein in the bacteria, which are very easy to grow in the lab. We only need 1/100th of a gram of the protein. That sounds like much, but for most of the biochemists, that's an enormous amount.
Then comes the really tricky bit. We want to grow crystals of our protein, and to do that we use robots like this. Basically what we're trying to do is to mix our protein with as many different chemical solutions as possible in order to try and find at least one that will allow crystals to grow. Using robots like this, we can test hundreds of screens at the same time.
It can take days, months, or even years for the crystals to grow. When the crystals are big enough, at least 1/10 of a millimeter in size, so still rather small, we shoot an intense beam of X-rays at them. And when you do that, an amazing thing happens. The crystal splits the X-ray beam into hundreds of separate rays that we record on the detector. Each ray produces a spot. Some are dark and some are light. They're arranged in strange, orderly rows. The pattern of spots looks nothing like the 3C proteins in the crystal, but it actually contains all the information that we need to calculate a detailed image of the molecule. The calculation gives us an electron density map. The map shows us the locations of all the electrons in the protein, and since the electrons define its shape, this reveals what the 3C molecule looks like. We end up with a fabulously detailed three-dimensional picture of the protein that we can rotate and examine at our leisure. The 3C protease from foot and mouth disease virus is one seriously complicated molecule. It contains over 3,000 atoms. To simplify our view of the protein, we often use cartoon representations like this one. Finding out the molecular structure of the 3C protease was a really exciting breakthrough. It helped us to understand how the protease works, but crucially, it also allows us to start thinking about how to design a drug that will stick to 3C and stop it from working, and so block the virus infection. Normally, the job of the 3C protease is to cut the virus polyprotein at defined positions. It does this by grabbing onto a particular stretch of the peptide chain, and it then uses some clever chemistry to break the peptide in two. So how do we make a drug? Well, from the work that we've done so far, we already have some very valuable clues about the particular molecular features of the peptide that the 3C protease likes to bind to. And what we need to do now is to design a molecule that looks like the peptide but is small enough in order to act as a drug. Here's what we're going to do.